Johnny here with Simpson Math. In this video, we're going to focus on the first derivative test and find if there is a change in increasing, decreasing behavior, where that change occurs. So right now we're under this big umbrella of curve sketching. So in previous videos, we've talked about, we should probably start off with talking about domain, the domain of a function. Once you have that in place, you can use limits to discuss vertical and horizontal asymptotes. The vertical comes from those domain restrictions. Horizontal asymptotes come from looking at the limit, the far ends of the function. And today I'm going to be focusing in on this first derivative test, change in increasing, decreasing behavior. And in order to do that, we're going to apply a first derivative test. So, first things first, I do want to mention domain because it is crucial for finding critical values. So I'm going to talk about the domain real quick. And I'm given here p of x, which is just a cubic. So this is just a polynomial. We're starting off pretty simple. So because I know polynomials so well, they have that, they're known for their nice curvaceousness. And in fact, they're known for their domain of all real numbers. They're not restricted in any way. I can plug any real value into that. Okay. Then I'd like to find critical values. Critical values come from the first derivative. So let's find p prime. Oh, polynomials are also famous for being easy to differentiate. So I can do several power rules here. I'll have 5x squared minus 8x minus 4, and the constant goes to 0. Two ways critical values may occur. One is any new domain restriction. So I had to look at the domain of the original function. I have to look at the domain again of the first derivative. Well, this is a quadratic, another polynomial. They're famous for being all real numbers. So there's no critical values yet, not from domain restrictions. Critical values, the places where change in behavior may occur, also occur at the roots of the first derivative. So I found the first derivative. Now I want to know, well, where does it touch the x-axis, if it does? I want to find the roots. So I can simply set that y, or the function, equal to 0, and solve. Okay, so I need to solve a quadratic equation. Several ways to handle this. I'm going to hope that it factors. Now, if there's a leading coefficient of non-1, I have to use what I call the AC method. So I'm going to do that real quick. 5 times a negative 4, I get this 20 value over here. And then I list all those paired factors. 1 and 20, 2 and 10, 3 doesn't go, but 4 and 5 goes. I've listed them all. I'm looking for 8, so that'll come from 2 and 10, as long as the 10 is the negative and the 2 is a positive. And I'm going to rewrite my trinomial as a 4-termed polynomial, replacing negative 8x with plus 2x minus 10x, and I still have that negative 4 constant. This is just how I factor trinomials. So I took that trinomial, I rewrote it as a 4-termed polynomial. Now I'm going to factor by grouping. From this first binomial, I can take out an x, leaving me with 5x plus 2. From this second binomial, or the second 2 terms, I need to take out that leading negative, and they're both even, so I'll take out a negative 2, leaving me now with a positive 5x and a positive 2. Factoring step's not done quite yet. I have this first term minus this second term, but those two terms have something in common, that 5x plus 2. So I'm going to factor it out from both terms. That leaves me with x minus 2. Okay, factored it. Now that I've factored the quadratic, I can set each factor equal to 0 and solve those two linear equations separately. So I'm just setting each factor equal to 0. I'll quickly solve. I get a -2/5 and a +2. These are called critical values. I have a critical value when x is -2/5 and a critical value when x is 2. That is, on my graph, on my original p of x graph, if there's going to be a change in behavior, it'll be when x is -2/5 or at x equaling +2. Okay, this comes into our next step, which is the first derivative test. I'm going to test the first derivative. All right, I'm going to draw a little number line. You may want to call that like a number line summary. This is just to help me keep me organized. And I'm going to put those two critical values on the number line in order. So I have -2/5 and I have +2. And in a previous video, we discussed change in behavior, that behavior theorem, where if the derivative, so down here I'm going to talk about p prime, if the derivative is positive, then the original function is increasing. If the derivative function is negative, then the original function is decreasing. So what I'd like to do is test. I'm going to plug in a value, something less than 2/5, like -1. I'll test a value between these two, something easy to calculate, like 0. And something bigger than 2, I'll try 3. And I'm going to test the first derivative. That is p prime of a -1. And what I'm doing here is I'm plugging in this -1 value into the first derivative. If my result is positive, then my original function would be increasing along that same interval from -infinity up to -2/5. If my first derivative pops out a negative number, and that means along that same interval, -infinity up into -2/5, I would be decreasing. Negative decreasing, positive increasing. So really, I'm not concerned with the exact value here. I just want to know, is this going to be a positive result or a negative result? All right, plugging in -1 into my first derivative. Just replacing all my variables with -1. Square it becomes positive. That's going to be +8. So it starts off, it looks positive to me. When I plugged in -1 into my derivative function, I got a positive number. That means the original function p is increasing at that point. So I'm increasing from -infinity up until -2/5. At -2/5, the critical value, that behavior may change. So I need to test a number between the two critical values. I'm going to test 0. Again, what I'm looking for is just the sign, S-I-G-N, if it's positive or negative. Well, 0 is nice and easy. That's really easy. This is going to be a negative. 0 kills those things, left with -4. So when I plug in 0 into the first derivative, I get a negative result, which means from -2/5 to 2 on the x-axis, my original function is decreasing. DEC for decreasing. At 2, I have another critical value. That's another point where I may change behavior. At this point, I could be decreasing forever or I may change again. I need to test a number beyond the critical value. I'm going to test 3. All right. 9 times 5 is 45, minus 3 times 8 is 24, minus another 4 more it's not going to be enough. This is definitely going to be a positive result. That's what I'm looking for. When I plug in 3 into the first derivative, I get a positive result, which means my original function was increasing along that same interval. So I can already give you a good sketch of what this function kind of looks like. With no points, I can tell you, starting at negative infinity, or even before that, I will be increasing. So in pencil here, I'm just kind of saying I've got this increasing behavior until I get to the critical value of negative 2/5. At that point, I change behavior. I'm no longer increasing. I have now turned around. I'm now decreasing until I get to 2, where I have another change in behavior, and I'll start to increase. And it's going to do that forever. So I can go ahead and even put arrows on there. Increasing, decreasing, increasing. That's the first derivative test. Now, depending on what you're looking for, that we may ask you this in several different ways. Maybe you're just curious with the intervals. So I'm going to answer that question. What are the intervals of increasing, decreasing behavior for P of x? Well, I just want that increasing, decreasing behavior, and I've answered this question already. So I went through the first derivative test, and I can see I will be increasing along the interval negative infinity up to negative 2/5. Union, I have another interval of increasing, starting at 2 and going up to infinity and beyond. I have an interval of decreasing between those two, negative 2/5 to positive 2. So that interval, I'm decreasing. Now, another question I may ask is, well, this is great and all, but I want to know where that actual point is, this turnaround point. So if I'm trying to graph this function, that seems like a very crucial point on my graph. Now that point has a name, not just a turnaround point, but a maxima. In this case, we call it a local maxima. That is, because I'm increasing and I turn around and start to decrease, in this little area, that's the highest the graph will be. I was increasing up to it, it's the zenith of the mountain, and then I start to go back down. So it's a little maximum point. And we call it a local maximum because if I were to start to zoom out, increase this interval, there may be another point out there that's bigger, higher. So I wouldn't call it like an absolute maximum or a global maximum, but I could definitely say it's the maximum value around here, a local maximum. Similarly, I can tell we're going to have a local minimum when x equals 2. Minimum value, bottom of a bowl, trough. So maybe I want to know those points. I want to plot those points on my graph because I'm trying to sketch this curve. Okay, well, if I want to find the local extrema, or the local maxima, that is just fancy for turnaround points. If I want to find the actual points, well, to find points, you just plug an x into the function and spit out a y, and you've got your xy coordinate. So I'm going to go back to my original function. I'm done with the first derivative test. I don't need to use that anymore. I'm going back to my original function. I'm going to plug in those critical values and just figure out what those y values are. So I'm going to evaluate p at negative 2/5. And then whatever the y value is, that's going to be that turnaround point. All right. Oh, that's a lot of fractions. Okay, just some tedious arithmetic. I think I'll just take it nice and slow. All right, so there we got. I'm gonna plug in negative 2/5 and get a 139 over 75ths out. So that's less than 2. So there we go. We have our local max at the point negative 2/5, comma 139/75. Now to go off and find the local min. Let's hope this one goes faster. I'm just going to plug in that other critical value at 2, so hopefully it comes out nicer. So we have when P of 2 is equal to negative 29/9. Whew. Okay, that's my local minimum at 2 comma negative 29/9. That's 3. 29/3. So if you're sketching a curve of the graph, you're going to want to, pinpoint where does that graph actually do the turning around. So hopefully their arithmetic is not so tedious. But I have a local max at negative 2/5, comma 139/75, and a local max at 2 comma negative 29/3. So yeah, now I should be able to graph it and give a good sketch. Increasing up to negative 2/5 at about shy of 2, 139/75. I will have a local max and start to turn around. I'll do some more algebra and later, clearly, to find the roots of the original function, but it'll cross 0 somewhere, and I'll come down to 2, and I'll turn around. This happens closer to like a negative 9 value, so way down here, negative 29/3. That's my local minimum. It'll turn around and it'll increase, and it's going to increase for now on. So I can go ahead and put arrows on here. So I can tell from here that P has 3 roots, and I need to go off and find them most likely. But that's the first derivative test with a nice polynomial. I think let's move on to another video where I do a harder example.